Hello, my name is Joseph Aerts, representing XML4Pharma, and this is our software demo as presented at the Phuse Connect Conference 2024 in Strasbourg. The goal of this project is to provide an extremely user-friendly software with a graphical user interface for the generation of CDISC, SDTM and SEND submission datasets that does not require SAS or R or any knowledge of their languages. It can be used by people with little programming experience, allowing the users to concentrate on SDTM or SEND skills. The software already has a lot of SDTM and SEND knowledge in it, guiding the users in the development of the mappings by the use of wizards. The software is based on define.xml templates, with all the mappings stored in the define.xml itself and keeping it synchronized with all the actions performed by the user. This also means that a near submission ready define XML comes as a free bonus. As the define.xml with mappings can be used as a template for another study, this also allows maximal reuse of mappings in other studies and projects. Okay, let's start the demo. The software comes as a Java application, meaning it can be used on any platform. First, we select an ODM file, usually coming from an EDC system. Even when one cannot obtain ODM, one can use the additional ODM generator software to generate ODM from almost any file type: Excel, CSV, SAS transport. Let us first inspect the contents of the ODM. We see that we have 5 visits. During the first visit, demographic information has been collected. Some of the items have a light blue background, meaning that they are annotated with SDTM or CDISC information. We see there is also a laboratory form used. For example, in the hematology section, we see the suggestion to map erythrocytes to LB oris with LB test CD equals RBC. Using the navigate button, we easily find out this item is collected in different visits. Let us now start with mapping. First, we need to select which version of SDTM or SEND we want to use and the CDISC controlled terminology version. We select SDTM IG 3.4 and define XML 2.1 and the latest version of the CDISC controlled terminology. It takes about a minute to load the template define XML. In the meantime, we can further inspect the source data. It is always a good idea to have a look at the captured data. For this, we of course need a file with clinical data. We see that the data for birth date is already in ISO 8601 format, so we will not need to transform these. We can also filter or add data for other items. Let us look at some other captured data points, erythrocytes. As erythrocytes is captured in different visits, we check generalize for all study events and also add leukocytes. These values indeed look to be concentrations. The tooltips give us some more information. The template define.xml has been loaded. It is also possible to load a define XML from a previous study as a template for the next study. This allows reuse of mappings. The cells are color-coded, red for required, blue for expected and green for permissible. We will start with DM by a drag and drop of DM to the bottom. Some first easy mappings can already be generated automatically. For example, the value of study ID can be taken from the ODM. And the value for domain is simply DM. We usually start with the required variables, for example site ID. As some of the ODM items are annotated, we can search for a hot mapping candidate. There it is. It is not a bad idea to have a look at the captured values. We can then just drag and drop to the SDTM cell for site ID. We do want to use the value of the clinical data, not anything else. The mapping script is then generated automatically. The upper panel provides an alternative way of selection without drag and drop. As in this demo, we will mostly be using drag and drop, we always hide it. Let us now develop the mapping for the SDTM variable sex. Also here, we can easily find a hot candidate for mapping. Let's have a look at the values in the ODM file with clinical data. We find that the values are already coded as F and M for female and male. And we drag and drop again. We again want to use the value, not anything else. Both in the source and in SDTM, the values are coded. In many cases, we can use the codelist mapping wizard. It has drop-downs on the right for the SDTM codelist values. We can use the Attempt one-to-one mapping button. It tries to generate a mapping based on word similarity. In this easy case, it works perfectly. The mapping script is again generated automatically. The next SDTM variable we want to map is race. By holding the mouse over the cell, we obtain some basic information. We can also display the CDISC nodes from the SDTM IG and even extend it with the information from the CDISC library. Again, due to the annotations, it is very easy to find the mapping hot candidate. Let us have a look at the captured source data. We drag and drop. We again want to use the captured value. And of course, we want to use the SDTM codelist. We will again use the codelist mapping wizard. and use attempt one-to-one mapping. As this is based on word similarity, it has mapped Caucasian to Asian, which is wrong. So we need to correct this. Strangely, other is not in the CDISC code list. We can save the mapping for Caucasian to white to the company synonym list, which we can then use in later one-to-one mapping attempts. The mapping script is generated. We correct the mapping for other in the mapping script itself. It's time to execute our mappings. We still have the ODM file with clinical data ready. We can take care that the maximal length for each variable is adapted to the longest value found. This is especially important when generating SAS XPT files. And we start the execution. The system asks us for which variables we want to have the length adapted. The XPT files are generated, but the results are also displayed in the internal viewer. Let's have a look at our generated dm.xpt file. As one sees, the lengths have been optimized for minimal file size. And here is the data. Of course, this is only a very first beginning. The next variable we want to map is country. When looking for a hot candidate, the system does not find anything suitable. But from the protocol, we know it is always USA, so we hard-code it. Of course, we need to assign protocol as the source of the data in the define.xml. For this, we use the menu Edit SDTM Variable Properties. We can also already set the length to 3 and set origin to protocol and source type to sponsor. If the source data was collected, we can also set the page numbers from the annotated case report form. But for country, we keep it to protocol and sponsor. We generate the SDTM again. When choosing for SAS XPT generation, some choices are automatically set. We also generate the mappings for DMDTC, date time of collection. The system doesn't find a hot candidate, so we will take the visit date and time. Let us first have a look at the captured clinical data. The date part is already in ISO 8601 format. That is fine. We also have the visit time. Let's have a look. Also, this is ISO 8601 compliant. So we drag and drop visit date to DMDTC. We indeed want to use the value, nothing else. and rename the variable to $date. Then we drag and drop visit time and append it as $time. The system warns us that the data type is not what is expected. We now have two variables, $date and $time. All we still need to do is to combine them to obtain the final mapping. For this, we can use the concat function. That's it. Let us execute the mappings again. As SASXPT treats datetime as character, we want to adapt the length. And here are the results. We now save the underlying define.xml to file, containing all the mappings, as we want to continue later. Here is our latest dm.xpt, optimized for minimal file size. Let us now do something less easy and set up some mappings for LB, laboratory. For doing so, we drag and drop LB to the bottom and accept to auto-generate some of the easy mappings. In general, we will always start with the mapping for the topic variable. In this case, it is lbtestcd. Let us look for a mapping hot candidate. The system finds erythrocytes, some others, and then also leukocytes. But only erythrocytes and leukocytes can be correct. We first drag and drop erythrocytes to lbtestcd. The system already understands that this time we don't need the value, but the identifier of the item. As the measurement was done for different visits, we need to check generalize for all study events. We also want to additionally include leukocytes, so add it to the selection. The system then asks us whether we want to use the mapping wizard, as lbtestcd has an associated code list. We choose mapping wizard, as the lbtestcd code list contains over 2500 items. It can take some time to set up the wizard. We can go for brewing a coffee or make a cup of tea in the meantime. In the wizard, we can either use the drop-downs to find the suitable values for lbtestcd or try the Attempt one-to-one mapping button. As we do not want to submit a code list with over 2500 codes to the regulatory authority, we generate and assign a subset code list. When using attempt one-to-one mapping, the system suggests RBC and WBC. That is looking good. The mapping script is again created automatically. It will select erythrocytes and leukocytes from the ODM by their identifier. Let us now start working on LB test. What we will often use is the menu View SDTM CDISC nodes in order to better understand what the variable is about. We can even extend it with information from the CDISC library. We could now repeat the same procedure as for LB test CD, but there is a smarter way. We can ask the system to use the decoded values from LB test CD. That is also much safer. Let us test our first mappings. Usually, during testing, there is no need to generate SAS-XPT files. We can once again ask the system to adjust the maximum length assigned. For integers, there is essentially no need to do so. Here are our first results. We see that there were many measurements. The natural order is to now generate the mappings for all BRS, the original result. We drag and drop from erythrocytes again. We again want to have results for every visit where erythrocytes were measured. And of course also from leukocytes. The system remembers these settings. The mapping script is again automatically generated. Let us test the mappings again. Just for the demo, we will generate SAS-XPT files again. We see that the results come into their natural order. And here is our lb.xpt file content. It is already optimized for file size. For the sake of time, let us now load a define.xml containing mappings for several domains. Also remark that a define.xml with mappings for one study can be used as a template for another study, meaning a lot of reuse. We replace the current define.xml with one that has many more mappings already. It takes about a minute to load. In the meantime, let us look at some other forms in the ODM structure. In our laboratory form, we have a section Hematology, but also another section Chemistry, only having the items LOINC code, result, unit and specimen. Let us have a look at the LOINC codes that were used. Once again, we want to have the data for all the visits. We can also combine that with the other items in the same section. We see that in some cases the specimen is provided, in other cases not. However, the specimen is also already in the line code itself. Another section in another form is smoking history. That will go into SU substance use. We can also inspect the metadata of the item. It is a boolean and has the SDTM annotation not submitted. But there is another item, number of cigarettes per day. From the data it looks as it is coded. So let us look at the metadata. There is also a section drinking. The annotation suggests that it will go into SU dose, with SUTRT is alcoholic drinks. In the meantime, our well-developed define.xml with mappings has been loaded. The values collected, however, are ranges, so we will need to use su.txt. We also already have mappings for AE, adverse events. Let us try to find that back in the source data. There it is. Adverse events has been taken as a repeating visit. For AE term, we see that there is a square on the icon, meaning that this is the mapping hot candidate. One can always generate a mapping completeness report to see which items were used in which mappings. This report can be saved and shared and discussed with other members of the mapping team. One sees that we have two instances of LB, one for hematology and one for chemistry. Let us have a look at the mapping for LB test CD for chemistry, as this is a bit special. The mapping uses the link to CDISC mapping, which is available as a RESTful web service for deriving the value of LB test CD from the line code. It was extended by us and currently contains mappings for about 10,000 line codes. There is a similar function for the LB spec, as the specimen is one of the dimensions of LOINC. And also for LB method. This also means that when the LOINC code is provided, generating the mappings to SDTM becomes extremely easy. As we now also have RFX ST-DTC, date time of first study treatment in DM, also LOB XFL, last observation before exposure flag, can be derived automatically. This is done in a post-processing step. What many people do not know is that the line code allows to do automated unit conversion from US conventional units to SI units and the other way around. Also for this we have a function available. It takes 4 parameters: the original result, the original conventional unit, the target SI unit and the line code itself. This function uses a RESTful web service from the US National Library of Medicine, NLM. Okay, let us execute all the mappings. We check the checkbox for the automated derivation of LOB XFL flags. The uniqueness of the test can either be based on a set of SDTM variables or better, on the LOINC code when available. As we want to generate size-optimized XPT files, we ask to adapt the lengths to the longest value found. In case we have unscheduled visits, we can also have the visit num for them being derived automatically. If necessary, as we have two instances of LB, we can also have a merged dataset created. Let's execute. In the Messages area, we see the responses from the RESTful web service passing by. Also, as we have two instances of LB, we want to have consecutive values of LBSAQ between the two LB datasets and in the merged one. For XPT optimization, we need to adapt the maximal lengths. The ones in red are the ones for which a higher length value must be taken, as otherwise there will be information loss. This is due to the way XPT works. Here are the results. For SU, substance use, and for AE, adverse events. For LB hematology, we mark the fully automatically assigned last observation before exposure LOBXFL flags. And for LB chemistry, where the SI unit results in LBSD-RESC and LBSD-RESN were fully automatically calculated thanks to the LOIN code. Here are the results for VS, vital signs. Also here, last observation before exposure flags were automatically derived. Let us now have a look at the generated XPT files. We see that also a sub-SU dataset has been created, with three non-standard variables: breath complaints, cough problems, and heart problems. Where does this data come from? For this, we need to take a look at our mappings for SU again. There, we see that three non-standard variables were added, just as if they were standard variables. Here is the metadata for breath complaints, with a yes-no code list. And similar for cough complaints and for heart problems. The reason that they have gone into sub-SU is that we checked the checkbox Move non-standard SDTM variables to sub. If we would not have done that, they would simply go into SU itself, which would lead to a non-compliant SU dataset. In this demo, I could only show you about 10% of all the features of the software. A compact list of the other 90% is shown here. On the SDTM-ETL website, however, you can find a lot of information, including a large number of tutorials. Thank you for your attention.